Hello everyone, welcome to my channel. Self, I am Deepak.R, studying in Sri Venkateswara College of Engineering from the Department of CSE Cyber Security. Today, I am going to explain about my topic, application on directional derivatives. Introduction to directional derivative. The directional derivative measures the rate at which a function changes along a specific direction. It used to find the slope of the function in a particular direction. The directional derivative is often applied in the field of such as physics, engineering, and computer science. Here, as shown in the figure, there are infinitely many directional derivatives of a surface at a given point, one for each direction specified by u as shown in the figure. The definition of the directional derivative. The directional derivative of a function f comma y in the direction of the vector v is equals to a comma b is given by the dot product of the gradient f with u. The formula for the directional derivative is directional derivative of f of x comma y is equals to del of f of x comma y into v. The directional derivative can be thought of as the projection of the gradient onto the direction vector. Finding the directional derivative. To find the directional derivative, we first compute the gradient of the function. Next, we normalize the direction vector by dividing it by its magnitude to obtain a unit vector. Finally, we take the dot product of the gradient and the unit vector to find the directional derivative. The directional derivative of the function f of x comma y at a point x naught comma y naught in the direction of the unit vector a comma b is written and computed as follows: du of f of x naught comma y naught is equals to dou f by dou x naught comma y naught a plus dou f by dou y x naught comma y naught b. We can write this as dot product du f of x naught comma y naught is equals to dou f by dou x naught comma y naught comma dou f by dou y x naught comma y naught in dot a comma b. We have unit vector u is equals to a comma b and the vector with the first order partial derivative. We call this second vector as the gradient. Physical applications. In physics, the directional derivative is used to calculate the rate of change of a physical quantity along a specific direction. For example, it can be used to determine the rate of temperature change in a fluid or the rate of change of pressure in a gas. The directional derivative helps in understanding the behavior of a physical system in different directions. Optimization problems. The directional derivative is crucial in optimization problems where we aim to find the maximum and minimum value of a function. By analyzing the directional derivative in different directions, we can determine the steepest ascent or descent or direction. This information helps us in finding the optimal solution efficiently. Computer graphics. Directional derivatives play a significant role in computer graphics, specifically in shading and surface rendering. They help in determining the rate of change of color intensity or brightness along the different directions on a surface. This information is used to create realistic lighting effects and shadows in computer-generated images. Gradient descent algorithm. The gradient descent algorithm utilizes the directional derivative to iteratively find the minimum of a function. It follows the direction of the steepest descent, which is the negative direction of the gradient vector. By updating the current position along the negative gradient direction, the algorithm converges towards the minimum. Sensitivity analysis. Sensitivity analysis involves studying the impact of small changes in input variables on the output of a mathematical model. The directional derivative helps in quantifying the sensitivity of the model to changes in specific directions. This analysis aids in decision-making processes by identifying the critical factors and their effects. Simulation analysis. The simulation is really just an expanded sensitivity and scenario analysis. Monte Carlo simulation can estimate thousands of possible outcomes based on conditional probability distributions and constraints for each of the variables. The output is a probability distribution for NPV with an estimate of the probability of obtaining a positive net present value. The simulation only works as well as the information that is entered, and very bad decisions can be made if care is not taken to analyze the interaction between variables. Next application is financial modeling. In finance, the directional derivative is used to measure the sensitivity of a financial instruments such as options or derivatives to changes in market variables. It helps in assessing the risk associated with different market scenarios and making informed invest decisions. The directional derivative enables investors and financial analysts to understand the potential impact of market fluctuations. And next, coming to the conclusion, the directional derivative is a powerful tool that allows us to analyze the rate of change of a function in a specific direction. It has numerous applications in various fields, including physics, optimization, computer graphics, and finance. Understanding and utilizing the directional derivative can provide valuable insights and aid in decision-making processes. Thank you for watching my video.